All right, we're recording now. So today we've got two different things coming at us. We have Descartes' rule of signs, and we have the rational root theorem. So Descartes' rule of signs is going to be able to tell us the possible number of positive and negative real zeros of a polynomial. And then the rational root theorem would tell us all the possible rational zeros of a polynomial. So if you've encountered something that you cannot factor, this is where the rational root theorem comes in handy. You can try dividing different things out, and it kind of tells you where to start dividing. But since we do have graphing capabilities, and in general, everyone's basically walking around with a graphing calculator in their pocket now, since we have the Desmos app and stuff like that. These are slightly less helpful unless you are not allowed a calculator. But anyway, it's good theory to know. So that's what we're doing. So grab your notes and let's get started. (2.4). This is the first day of it. So we've got the rational roots theorem and Descartes' rule of signs. Okay. Rational roots, Descartes' rule of signs. So we're going to start with the rational roots theorem. Okay, so the rational roots theorem says that the list of all possible rational zeros is equal to the factors of the constant term divided by the factors of the leading coefficient. So it's the factors of the constant term divided by the factors of the leading coefficient. So we're going to talk two examples here. The first one, f of x equals x to the third minus x squared minus 8x plus 12. Okay. So first we have to identify what is the leading coefficient and what is the constant term. The constant term is that one on the end that has no x attached to it. That's our constant term. And then the leading coefficient, of course, is the number in front of the highest power of x. So in this case, it's 1, since it's 1x cubed. Okay, so we have our leading coefficient and we have our constant term. So now what we want to do is list all the factors of the constant term and all the factors of the leading coefficient. So the leading coefficient being 1 here makes our life easy. Factors of the leading coefficient are just plus or minus 1. Factors of the constant term, however, this one has quite a few more factors. Of course, 1 and 12, and it's always plus or minus. So plus or minus 1, plus or minus 12. And then 2 and 6. 3, and 4. So those are all the factors of my constant term. So now what we want to do to figure out all the possible rational zeros is take the factors of the constant term and divide by the factors of the leading coefficient. So so the possible zeros would be plus or minus 1, plus or minus 12, plus or minus 2, plus or minus 6, plus or minus 3, plus or minus 4, all divided by plus or minus 1. So that means that each of these individually is being divided by plus or minus 1. And the nice thing about it, the leading coefficient being 1, is that that means my possible zeros is really just this top list here. These are all my possible zeros. So the things that I would check would be 1, -1, 12, -12, 2, -2, 6, -6, 3, -3, and 4, and -4. Those are all my possible rational roots. So the annoying thing is that if you were supposed to go and find the zeros or find the rational zeros based on this, you would have to check all of these until you find 3 that work. But the nice thing is that we have graphing calculators. So you can also go and graph and find out exactly which ones are the rational roots without having to check each and every one of these. Because to check each of these, you would have to divide by, x minus 1, and then divide by x plus 1, divide by x minus 12, divide by x plus 12. You'd have to divide each of those things out to try and determine what the roots are. Or you could factor the thing. If it's something that factors nicely, like this one, I believe, does factor nicely. So in this case, you could try factoring. But yeah, finding all of the zeros using the rational roots theorem is not all that helpful when you have something that has a lot of factors. If your constant term is something that doesn't have a lot of factors, then that's another case where it would be might be easy to find the roots using the rational roots theorem. And keep in mind, this is just the rational roots. So remember, rational numbers can be written as a fraction. So if you have an irrational root, like the square root of 2 or something, then the rational roots theorem is not going to help you to find that root. So keep in mind, this only helps us find the rational roots. Okay. Let's see. Now, what if we had something else, like, what if the leading coefficient wasn't a 1? What if we had two x to the 4th plus 3x squared minus 6? And we wanted to list the possible rational roots. Well, then we'd have to, okay, the leading coefficient here is 2. And the factors of 2 are plus or minus 1 and plus or minus 2. The factors of -6 are plus or minus 1, plus or minus 6, plus or minus 2, and plus or minus 3. Those are all the things that multiply to 6. Or to -6. So to find our possible rational roots, we take these and put them on the top. So plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3. And then on the bottom, we have plus or minus 1 and plus or minus 2. So this means that all the things we would have to check, we'd have to check 1 over 1, 1 over 2, 6 over 1, 6 over 2, 2 over 2, or sorry, 2 over 1, 2 over 2, and 3 over 1 and 3 over 2. So we have to divide each of these individually by the things on the bottom. So we have to check plus or minus 1 over 1, which is plus or minus 1, plus or minus 1/2, plus or minus 6 over 1, which is just 6, plus or minus 6 over 2, which is 3. Plus or minus 2 over 1, which is just 2, plus or minus 2 over 2, which is just 1, which we've already listed, plus or minus 3 over 1, which is what we've already listed as well with 6 over 2, and then plus or minus 3 over 2. So these are all of our possible rational roots here. So it does take a little bit more work when your leading coefficient has more factors. So you have to divide each of these things by both of the factors. Okay. So let's have you guys try one. List all possible rational roots of f of x equals 3x to the 4th minus 2x squared plus 6x. We'll go minus 4. Once you think you have your list compiled of all possible rational roots, type Friday in the chat. Alrighty, if you got plus or minus 1, plus or minus 1/3, plus or minus 4, plus or minus 4/3, plus or minus 2, and plus or minus 2/3, you are correct and have your complete list. If you did not, take a look which one you missed and add that to your list. Okay, so that is the rational roots theorem. The next thing we're going to talk about, once I get a new piece of paper, is Descartes' rule of signs. So Descartes' rule of signs is designed to help you find how many positive and negative real zeros could be existing for that function. So Descartes' rule of signs is next. I'll move that up. Descartes' rule of signs. Okay. So for Descartes' rule of signs, oh, come on, paper. There we go. The number of positive real zeros is equal to the number of sign changes of the coefficients of f of x. Or less by an even number. So the number of positive real zeros of f of x is equal to the number of sign changes of the coefficients of f of x or less by an even number. And then the same thing is true for the negative real zeros, except for it's with f of negative x instead of f of x. So for negative real zeros, the same is true, except we use f of negative x to determine it. Okay. I'll give everyone a moment to write that if you're writing it, and then we will do an example because this rule really makes a lot more sense when you're dealing with an example. Okay, so here's our example. We have g of x equals negative 3x cubed plus 2x squared minus x minus 1. So what we're doing here is to find the positive or the possible number of positive real zeros is we have to count the number of sign changes. So for example, this one, it starts off with a negative coefficient, and then the next one is positive. So from here, we are changing from negative to positive. And then the next coefficient is negative. So then we're changing from positive to negative. And then the last one remains negative, so it's not changing. So this one has 2 times where the sign changes. So 2 sign changes tells me that that g of x has 2 or less by an even number. So if I could have 2 or 0 positive real roots. So 2 or 0 positive real roots, since we had 2 sign changes. If it had 3 sign changes, it would be 3 or 1. If it had 5 sign changes, it would be 5, 3, or 1, because you're going less by an even number each time. If this had 4 sign changes, it would be 4, 2, or 0 positive real roots. So that's positive real roots. Then to do negative real roots, we would have to find g of negative x. So that means I need to plug negative x into this function for x. So we'd have -3 times -x to the third plus 2 times -x squared minus -x minus 1. And then I want to go through and simplify this. -x to the third is going to be a negative number. A negative times a negative is a positive, so this becomes 3x to the third. A negative number squared is a positive number, so this is the same as 2x squared. Minus -x is like adding a positive, and then minus 1. And then we would go through and do the same thing, counting the sign changes. So from here, we're positive, 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 negative. So we've got one sign change here from positive to negative. So one sign change tells me that g of x has one negative real root. One negative real root. Okay. And the cool thing is we could go and check this if we used a graphing utility like Desmos or something. Okay, so if we were to graph g of x is -3x to the third plus 2x squared minus x minus 1, we see that this has one negative real root and it has no positive real roots, which fits within what we expected from Descartes' rule of signs, because we could have either 2 or 0 positive real roots, and it told us we were going to have one negative real root. And that does work out here. Okay. Yeah, we're going to do another example of this. Because yeah, this one takes a little bit of getting used to, especially with plugging in the -x. That tends to be something people have a bit of a hard time with. So let's do another. Okay. So this time we're going to say f of x is 4x to the fourth minus 13x to the third minus 21x squared plus 38x minus 8. Okay. Gonna write that down. So for this one, we want to count the number of sign changes. So on your own real quick, count the number of times the coefficients change signs here. And once you think you've got it, type that number in the chat. How many sign changes do we have? Good. We can recognize the sign changes. There are 3. One here, and one here. 3 sign changes. Okay. So how many positive real roots could I have here? What does that tell me? Is it just 3, or is it 3 or something else? Yes, 3 or 1. So this tells me that f of x has 3 or 1 positive, spelling is hard, positive real roots. Okay, so 3 or 1 positive real roots. Now we want to plug in f of negative x. So we're plugging in negative x to the f of x function. 4 times negative x to the fourth minus 13 times negative x to the third minus 21 times negative x squared plus 38 times negative x minus 8. Okay, so try simplifying this one on your own real quick. Figure out if it's going to be a positive or a negative overall. We'll give you a minute to try that, and then we'll talk about it. Yes. Yeah, so keep in mind, anytime you have a negative number to an even power, it's negative. Anytime you have a negative number, or sorry, to an odd power, it's negative. Anytime you have a negative power to an even number, it's positive. So if you're looking to check your work, this is what we should get to simplify this. It's 3 or 1 because it's less than that by an even number. So it's less than that by 2 or 4 or 6. So when at whatever you get here, you subtract 2. So like 3, you would subtract 2 to get 1. So we have 3 or 1 positive real roots. If we had 2 sign changes, it would be 2 or 0. If we had 4 sign changes, it would be 4 or 2 or 0. If we had 5 sign changes, it would be 5, 3, or 1. So it's yeah, less by multiples of 2. Yeah, if it was 7, then you would have 7, 5, 3, or 1. Yep. All right, so for this one, how many sign changes do we have here? Yep, just 1. So that means it has 1 negative real root. Okay. So we get 3 or 1 positive real roots and 1 negative real root based on Descartes' rule of signs. Okay. So let's see. Before we get our assignment for today, on a scale of 1 to 5, how do we feel about Descartes' rule of signs and rational root theorem? 5 being, I'm so ready, let's give me the homework. 1 being, you could use some more examples. Okay. Looks like most of us are ready to roll. In that case, I will post the assignment. It is IXL again. And then we'll kind of go from there. Chill out, computer. Okay, so we got two IXL sections, one on the rational root theorem, one on Descartes' rule of signs. Rational root theorem one looks like this. Polynomial with integer coefficients, it tells you the leading coefficient and the constant term. And so then you have to select which of the following could be rational roots of g of x. As we go through this, it'll ask similar questions with different leading coefficients that might have more factors and more combinations of factors possible. And then let's see, on this one, important announcement for this one, for D6, we are going to go to 90 because we do want to be able to pick it out of an actual function as well. So we are going to go to 90 on D6. I'm going to update that here. And then Descartes rule of signs ones looks like this. So according to Descartes' rule of signs, could this polynomial have exactly 3 positive real zeros, including repeated zeros? Choose your answer based on the rule. So you just have to figure out the number of sign changes here. Ender, chill, dude. He makes weird noises. Okay. So you would decide, okay, this has 1 sign change here, another one here. There's only 2 sign changes, so no, this could not have 3 positive real zeros. And then we've got negative real zeros, negative real zeros. Okay, so stick around if you have questions. I will post an exit ticket some point towards the end of class. Otherwise, you are free to head on out and enjoy your weekend.